This is a supplemental lecture on techniques in interpreting mass spectroscopy. I want to provide a couple examples of how mass spec fragmentation data can be interpreted, and this should be hopefully useful for you as you start to interpret your own data. I just want to mention here briefly about mass spectrometry. I want to mention what exactly is being measured. And this instrument here is measuring the masses of ion fragments. These are generated in the gas phase. So when the sample is introduced into the inlet of a mass spec and it is ionized. And the general scheme of what happens is some compound that has some given mass gets accelerated in the presence of basically an electron gun. This is called an electron multiplier. And what it does is it shines a beam of electrons across and it specifically knocks one electron off of the compound with a given mass. And what it turns into is called the molecular ion. And the instrument is capable of measuring the mass to charge ratio. So it's this index here, m over z. And typically, in small molecules, z equals positive 1. It's possible to have multiple charges placed on a molecule, but for most of the practical purposes and in this discussion, we're going to assume that it follows this general scheme, and the charge is 1. So when the charge is 1, the mass to charge ratio equals the mass. So in essence, we are scanning all of the masses of all of the fragments that exist. So I want to pull up an example here, and I just pulled this off of the NIST webbook. This is the mass spectrum of water. And if we look at the mass spectrum of water, I see a peak here at 18. I also would see a peak here at 17. I want to look at these axes here. I have relative intensity on this axis, and I have mass to charge on this axis. And so this is essentially counting the number of ions that are observed. It takes the ion that is observed the most, it sets it to 100, and we call this the base peak. Okay, so whichever one is 100% relative abundance. It may be the molecular ion, it may not be the molecular ion. We don't really know. But by definition, the base peak is the highest one. And then we count all the masses relative to that base peak. And so I'd look at 17, and I would see that that's at approximately 20. So about 20% of mass to charge 17 is observed compared to 18. Now, we know the structure of water, H2O. What would this ion have to look like in order for us to observe this in the mass spectrum? Well, water would have to be introduced into the instrument. It would have to have one electron taken off of it. And we would have to place this somewhere. So there would be a charge and there would be a radical. Okay. And if we were to count each of these up, I know that oxygen is 16. And hydrogen is 1. And so when I add these all up, I would get mass to charge of 18. Where is this placed? Well, usually you place the radical at the position that can hold the charge and or the radical the best. So whichever part of this is the most stable. Obviously in this situation, hydrogen isn't going to hold the radical very well. And so we see this one commonly. So you see a little bit of 17. What happens with 17 is we have water, when it's been introduced, is going to have a mass to charge of 18, and we get a loss of a hydrogen radical. So if I have OH here with a positive charge and I have hydrogen radical, I can count the mass of this ion. And this one here is mass to charge of 17. We don't see the hydrogen radical because the instrument is only capable of looking at ions. It's only capable of sorting things by the mass to charge ratio. And if it has no charge, then the instrument doesn't see it. So the hydrogen radical we don't see. Like we saw with the case of 17, we very commonly observe that the ion can decompose further. So I want to pull up a spectrum of another molecule. This one is going to be methanol or methyl alcohol. And we'll use this in our discussion here. So I'm going to cut and then I will paste it right here. So this is the spectrum of methanol. Now, when I'm looking at this, I'm just trying to identify what these peaks are and what the masses are that they correspond to. Here, this is 32. This one here is 31, and that's what I'm seeing at a very high as a base peak with 100% relative abundance. Here I'm also seeing 29, and if we look out here, I guess we can look at the smaller one. We can look at this one at 15. And so the relative abundance is directly proportional to the stability that we see. And so the more stable of these ion fragments you get, the more of it you are going to observe. So now we need to go back and look at our structure of methanol and ask ourselves, how could this molecule fragment in a way that gives us this mass spectrum? So this data is empirical. You have the data, and now you need to go back and look at the molecule and figure out how it all goes together. In other words, methanol had to combine with one electron in the instrument to form methanol, which has a radical and a positive charge. It's also going to have lost an electron. So we see that it goes from electron to 2 electrons here. When I look at the mass here, I just count each of these up according to the masses of each of the elements. Carbon is 12, hydrogen is 1, oxygen is 16, hydrogen is 1. And so when I count each of these up, this makes a mass to charge of 32. Okay, and that's going to explain one of the peaks that we're seeing. But we can call this pretty definitively, we can call this one at 32 our molecular ion. Now we need to come up with some other ways that this molecule can fragment. So I'm going to write up the molecular ion, and we're going to see a number of different ways that this can further decompose. This can decompose into the following: cation plus a hydrogen radical, like we saw in the previous example with water. So if we lose one hydrogen off of this, now this is going to have a mass to charge of 31. Now you see this is the base peak. This is probably going to indicate that this is the most stable of each of the fragments. But as we're going to see, there's other fragments that may exist in different abundances. This molecular ion could further decompose to form a methyl cation and a hydroxyl radical. And keeping in mind that the instrument only sees ions, we're going to count the one that has the cation. The methyl cation has a mass to charge of 15. And so that's what I'm seeing over at my 15 signal. What could be 29? 29 is an interesting case where we see the fragment decompose further. So let's look here at the ion that I have. And I'm gonna highlight this ion that I'm talking about, this yellow one right here. This one can further decompose to this ion, which would be following, plus H2. So we see that you can get a hydrogen off of each of the corresponding of the adjacent atoms that can give you ions that appear in your mass spectrum. This corresponds to 29. You may be asking yourself, what can I do to start interpreting this mass spectrum when I get it? Because it can be very overwhelming just to collect data and to see a bunch of mass fragments in different relative abundances, but not really have any idea about where to start interpreting this spectrum. So I want to come up with a standard procedure that we commonly use when we're interpreting our mass spectra. So the first thing that I'm always doing is I'm looking at the molecular weight of my molecule. Okay? The molecular weight of the molecule is going to directly feed into the mass of my molecular ion. I'm interested in the elemental composition. How many hydrogens, how many carbons, how many oxygens, how many nitrogens are present in this molecule. And I'm also interested in the degrees of unsaturation that are present. How many rings and or pi bonds exist in this molecule. This can give me quite a bit of information on the molecule, and that's going to be the first step that I can use to start classifying this further. Once I know that, I'm going to start looking at substructures that are present in the molecule. I'm going to be looking at other little pieces and substructures that exist on the molecule that could correspond to those little mass fragments. Sometimes you see some more often than others. For instance, 43 is a very common one with compounds that have an acetyl group. You're going to see some of these common substructures. And then we're going to look at the connectivities of these substructures. Okay. And once we have this in mind, we will then have a postulated possible molecule. And this corresponds to the mass fragments that we observe. So let's try this standard procedure out for another example here. And what I've done is I have a molecule here that's an unknown. I have no idea what this is. I have introduced this into my mass spectrometer. I am sure that it is pure. That's always a given, or at least an assumption you should make, is that this molecule is going to have purity, and I need to go through this procedure here in order to determine what this looks like. When I'm looking at this molecule, or when I'm looking at this fragmentation pattern, I'm going to see here that I have a 34 is present. I see that I have a 33 that is present. And I'm going to look down here, I'm going to see I have a 15 that is present. Well, like we had in the last example, there was a methyl group that fragmented off, and I had a methyl cation. And so I'm going to kind of keep this one in mind here, that 15 probably, it may not always be the case, but 15 I commonly see that as a methyl cation. Now the next thing that I'm going to start looking at is the relative shifts between these two masses. If I'm looking at the high peak here, 34, and 15, I'm going to ask myself, what is the difference between those two? So I'll take 34 minus 15, and I find that this is 19. And what could correspond to 19? I go in and look at my periodic table, and I find that this is fluorine. So we have fluorine 19 that could be present in our sample. I'm also looking too at other shifts. I'm looking at, for instance, 33. So to go from 34 to 33, that probably involves the loss of a hydrogen. So using this information, we can probably come up with this. If I have a methyl that's present and I have a fluorine that's present, I know that fluorine forms one bond, and so it probably makes sense to come up with a molecule such as this. Once I come up with the molecule, now I need to go back forward and run through that whole postulation procedure. What would this look like once it is introduced into a mass spec? So I would have fluoromethane would look like this. this would have a mass to charge equal to my molecular ion, 34. But I also need to think about how could this fragment. Okay, well, there's a couple ways that this could fragment. One would be if I lost a fluorine, I could get a methyl cation plus a fluorine radical. Or if I lost a hydrogen, I could have the following cation. Because I'm seeing the relative abundance of these two very plainly, I'm seeing 15 is significantly lower than that of 33. This top one here is mass to charge of 15. This one here is a mass to charge of 33. So I'm seeing 33 in significantly higher abundance, and so that probably is telling me that 33 is more stable than 15. And if we were to draw out this molecule here, I'd see two hydrogens, I'd have a positive charge, and then I'd have fluorine, which has 3 lone pairs of electrons. And indeed, there's a way that this molecule can be stabilized through resonance. So I would look at this, and I would see that I would have a possible resonance stabilized cation. And that can explain for the spectra of mass to charge of 33. Both of these are mass to charge 30. Both of these represent a mass to charge of 33, and so that's what I'm seeing in the spectrum. Another tool that's really helpful in interpreting your mass spec fragmentation pattern is using a ChemDraw, and I want to demonstrate how to use that with the molecule of neopentane. Now, neopentane, I'm going to pull up the mass spectrum off of NIST, and I'm going to cut and paste it into place here. And when I look at neopentane, I notice a very large signal present here at mass to charge of 57. If I look at neopentane, the structure of the molecule here is this one. It's 2,2-dimethyl propane. And if we were to create a molecular ion, as indicated in a fragmentation pattern, we know that the molecular ion should be found at a mass to charge of 72. But yet I am not seeing anything like that in this region. Where is 72? Well, it turns out that 72 is in such small abundance because of its relative low stability. So when we're looking at this, I look at the shift between the two, and if I look at between 72 and 57, I see that is M minus 15, which is typical of a methyl fragmentation. I can show this by going over to ChemDraw, and let me go over to the program, and I have a molecule of neopentane already built up. You need to build this on your own time, but there is a little button over on the side here that says Fragmentation Tools, and when I click it, it creates a cursor that I can press and drag. And if I drag, you see it creates this little dotted line, and I can drag it through bonds. And if I drag it through this carbon-carbon bond, you can see the two masses of the two fragments that would be formed. And so forming one is a methyl radical, forming one with a C4H9 radical would have those masses. Now when I let go, it's going to put those two radicals together. The program lets you piece together where the radicals go and where the cations go because it's not familiar with your specific system. So you have to piece those two together, or you can just kind of go through and put the line through different bonds and see what the masses of those different fragments correspond to. So here I see a 15 and I see a 57, and that's something that I should be seeing over here. I see a 57, and that's consistent with what I would expect for neopentane. I want to talk a little bit more about some of these more complicated, mass spectrum that you will more than likely observe. And these mass spectra have to do with alpha cleavage, or breakage at the alpha position. One example I have is with 3-pentanone. 3-pentanone has the following chemical structure. And if I was to pull up the mass spectrum of 3-pentanone, it would look like this. And I'll paste this into place right here. So with 3-pentanone, I'm seeing a few pieces. I'm seeing if I was to add up all of these, I'd see a signal here at 86, and I'm also seeing a signal here that is present at 57. Okay, so the big question is, where did these come from? Again, we're going to run this fragmentation pattern. We're going to bounce an electron off of the molecule, and we're going to create the molecular ion. And because the oxygen has several lone pairs, I'm going to put that radical at that position here. And now we're going to see that this compound can fragment off according to the structure of the molecule. Now what this is a radical. There is a cation, and so I can actually break those bonds here at the alpha position. I can break with one electron from that bond going into the oxygen. One electron from the radical of that oxygen can come together. What this does is form a triple bond between the carbon and the oxygen, and it breaks the carbon-carbon bond at the alpha position. So I want to draw the structure of this molecule. I have now a triple bond between the carbon and the oxygen. I've retained the positive charge on that oxygen, and what I have left is the ethyl radical. Okay, now I add up all of the masses here, and the masses that I see here are 57. The ethyl radical is not seen because there is no charge on the molecule, and so that's accounting for the masses that I see, along with the mass to charge of 86, which corresponds to my molecular ion. Another molecule that we can find that fragments a little bit differently is 1-butene. 1-butene doesn't have an oxygen to put this radical onto. And so when the molecule is introduced into the mass spec, it is the double bond that winds up breaking. And so I create what is called a dystonic radical ion. In other words, I pull one electron off of that pi bond, and that creates a radical, and it creates a cation. Now the radical's got to go to one atom, the cation has to go to another cation, or the cation has to go to one atom, and the radical has to go to another atom. And then the molecule is going to rearrange spontaneously in a way that is going to allow the molecule to get the most stable. So this mass here is going to correspond to my molecular ion, 56. And if I go pull up the spectrum of 1-butene, I should be able to find the 56 present in there, and I do. Let me paste this in place here. I see a 56 present, but I'm also seeing this other one present at 41. So how can that correspond? Well, we want to make sure that we can show how the methyl radical is cleaving. The way that this radical cleavage occurs has to do with creating a new carbon-carbon double bond. I'm going to create a new pi bond at this position, and then I am going to fragment an adjacent carbon, or the alpha carbon. And I'm going to push from that single bond, I'm going to push the electrons into the peripheral carbon. And when the reaction occurs, what's left is I have a methyl radical, and I have now created an allylic cation. These are resonance stabilized, and so they are very, very stable. And this is, when I count them up, corresponding to the mass to charge of 41. The last example that I'll talk about is one that you will see commonly with carbonyls, those that contain ketones, aldehydes, carboxylic acids, esters, amides, etc. These compounds can undergo what is called the McLafferty rearrangement. And the example that I want to use here is the following molecule. This is an ethyl ester of butanoic acid. So this is ethyl butanoate. And I'm going to pull up the spectra. And I'll put this into the notes. Paste right here. And the first thing that I notice with this is I should be able to count up the masses of, the mass of my compound. This should, as a molecular ion, have an electron here that I have eliminated from the molecule. This is going to create a molecular ion with a mass to charge equal to 116. And if I look on the molecule here, I see this one here. This is at mass to charge of 116. However, that's a pretty small fragment that I'm seeing in the spectra. There are other larger fragments that I can see. One specifically that I'm interested in is I see 88 that is present at this position, but I also see 71, and I also see 43. So I want to come up with a pattern of fragmentation that makes sense for each of these. Now what I'll see in each of these molecules is I'm going to look at these peripheral atoms here, and the hydrogens that are bound to those carbon are actually going to come into play. And so I'm going to redraw this molecular ion with the methyl group kind of shown in a different position. But hopefully this illustrates why this happens. I'm going to put the hydrogen up at that position. And this is important because you can see a six-membered ring is potentially forming. This is very stable transition state, and so this molecule rearrangement can happen spontaneously. So in other words, the radical off of the oxygen grabs a hydrogen and it pitches the radical electron directly into that carbon that is at the gamma position, with this being the alpha carbon, this being the beta carbon, and then this carbon here being the gamma carbon that is 3 bonds away from the carbonyl. So the reaction here leaves the following radical, and the oxygen now takes the positive charge. So now this molecule is in a position to rearrange the same way that we showed the previous example. Only difference is that we're going to find a neutral loss. So this can form a double bond if the bond between the alpha and the beta carbon break, and it's going to pitch the electrons from one of those bonds into the alpha carbon. So the structure of this involves creating a neutral loss. In other words, this creates ethylene, and it creates the following stabilized radical here. And I should put a hydrogen onto this oxygen and put a positive charge. And when I look at this mass, this is a and I count this up, it's a mass to charge of 88. We also see there's another way that this can react if it's the other carbon atom. If I take the one on the right-hand side of the parent ion over here that I'm indicating with a green arrow. So I'm going to write that down. In a conformation that could potentially create a three-membered ring. Again, this oxygen is a radical. It has a cation when it's in the molecular ion form, and this is fragmenting further. That oxygen grabs the hydrogen off of the other side and follows a fragmentation pattern similar to the one we just talked about. So I'll put an oxygen here, and I have a radical out peripherally. Now it undergoes the same reaction that we talked about in this previous reaction, only it puts a radical at the oxygen. Whereas in the previous example, it was at the carbon. So we would form the following molecule, which is going to have a similar mass to charge ratio, resulting in the same neutral loss. And this is also a mass to charge of 88. Okay, well, 43, where did that 43 ion come from? I want to go back to one of these mass to charge of 88. So I'm going to look at this one here to give me my best explanation of where this 43 ion is generated from. And this, I'm going to write out off to the side. The oxygen is protonated, so it carries a positive charge. I have an oxygen adjacent, and I have a radical on the carbon. And so I'm just redrawing that mass to charge 88 species from before. So this can form a new carbon-carbon double bond if the other adjacent atom breaks. And we're going to pitch the electron up into the oxygen to create an ethoxy radical. And the structure of the product winds up being this one. Positive charge here, and we get a charge migration. This accounts for the mass to charge of 43, and we put the radical onto a different species. And again, the radical is not seen by the instrument because it doesn't have a charge. So this is a pretty good primer for the types of reactions that you're going to experience when you collect your data. Oftentimes it's difficult to interpret this, but if you follow these general rules, it should give you a good starting point. Any further more advanced interpretation of the spectra is probably best to check with your instructor about and ask and be in touch with them as you go along. So good luck in interpreting your spectra. I hope that this was helpful.